genetic engineering tool they've been developing and using as data.
Okay, thank you. And first, thank you for inviting me. It's nice to be here. Thank you, Yap. Yeah, so as Yap said, I'm going to be talking about a tool called LAM that we've been working on for the past few years. So I've, until recently, been the primary developer of this tool. I've now, over the last 6 months or so, switched from being a developer to a user, so I'm going to be talking also about some of the uses of this tool. And yeah, so LAM is primarily aimed at creating reusable real-world semantic models, and I will explain what that pretty bombastic title means. Yeah, this is joint work with Cathy Gray, Scott Owens, Peter Sewell and Tom Ridge, who are spread out over various universities, and also various other people who've filed bug reports and issued pull requests and so on. Okay. Oh, sorry. Okay, yeah, so recent years I've seen quite a major interest in real-world semantics. So what I mean by these real-world semantics is the formalization of memory models, microprocessor architectures, virtual machines, language semantics, and so on. So these are usually used as subcomponents in large proofs of correctness. So some of you may have heard of, say, COMSERT or KKML or SOAR or CHERCO, say. So all of these verified compiler efforts need a verified machine model, a machine model at the base, validated against real hardware, and tested, well tested, and so on. So by academic standards, these models tend to be quite large. So tens of thousands of lines, not hundreds of thousands like you get in industry, say. They're written by multiple authors, perhaps working across multiple sites. Say if you're on a European project, you'll be working, say, with 3 sites, all working on the same project, on the same bit of code. So despite the increased demand, the methods that we use to build these models haven't caught up, and the techniques that we're using are still fairly rudimentary. So as these models are typically used in formal proof efforts, they're mostly developed inside the logic of a theorem prover, like Isabelle Hall, Coq, Hall 4, Hall Light, say. Or if you'd be really fancy, you'd develop them inside programming language like OCaml or Haskell, test there against real hardware, and then hand port into the logic of your theorem prover once you're satisfied that the model actually matches the real machine. Now this porting may be machine assisted, but it's assisted with sed or Perl scripts. There's no actual formalized technique for moving a model written in one language inside a theorem prover. Now, as a result of this lack of tooling, there's no library of off-the-shelf components. So if you're writing a new verified compiler, if you want to do COMSERT 2, say, you can't just go and find a model of the ARM architecture written inside your theorem prover of choice. You can't go and find, say, a Coq model of the Java memory model. They tend to not exist. So as a result, because people often want to get to the main thrust of the project, only small fragments of models tend to be written. So again, come back to COMSERT. If you look at what they did with the COMSERT backend, they were targeting the PowerPC architecture, but they were only formalized the machine instructions that they knew that the compiler was going to emit. They didn't actually formalize the entire PowerPC machine architecture. And also there's a lack of validation. So typically you write a model and you spend more time testing against hardware boards and talking to the architecture experts about what this model is actually supposed to do than you do spending writing the model in the first place. Now another another issue is that there's often a close coupling between the people who build the models and those who eventually use them. There's not a distinct class of people who are specialised in writing machine models, memory models, and so on, and people and consumers. So as a result, there's not very much documentation because the people who are writing them know how to use them anyway. So you may think that I've got put down on proof assistance, and that's not true. I really like proof assistance.
Is this the order?
No. There's no Cambridge bias here. Yes, I really love Isabelle, Koch, Hall Light, Matita, ACL2, U-Pearl, and so on. But the main problem is that everybody is an expert in a different system. And it takes time, and on an academic project, time is money, to get people up to speed. If you hire a new postdoc who's an expert in Hall 4 and you've got an Isabelle model, they need to invest some time and money to get them up to speed with that system. And you have to know the idiosyncrasies of various proof assistants. So the precise behaviour of Isabelle's simplifier is a black art, and you can spend years trying to work out what that does and never come close to being an expert in that. And the same is true with issues in Koch related to termination of functions and tactics and so on. So as a result, you have theorem-proven lock-in with these models, where if you write a model in Koch, you can't easily get it to the Isabelle community. They just can't use it. And this leads to a duplication of efforts, and as I said, a lack of validation. So, I mean, it would be really, really nice if we could demand that everybody just use Isabelle or Koch, but that isn't going to happen. It's the quickest way to start a holy war. Perhaps a debate over Emacs and Phi comes close, but yeah, it's just not realistic to demand that everybody switches their chosen foundational system to a competitor. So this is just a small case study of an existing model, the workflow that my colleagues at Cambridge, although most of them have now left, had to do before LEM existed. So this is the C++11 relaxed memory model, and yeah, it's by this group of people back in 2011. So it was originally written in Isabelle, and the model itself was in a theory file, atomic.theory. And there was also an accompanying theory file called code.theory, which had various commands telling Isabelle how to extract this model into standard ML or a camel, so we can be validated against the real C++ programs. Now, from the atomic theory file, you could execute slowly within Isabelle on some very small examples, and you could also use a tool called nitpick, which is a counterexample checker to test various properties. So using code.theory, you've got some extracted ML files, and using an ML compiler, you could link these with some existing handwritten ML files to get CPP-man, which is a tool for stepping through all the allowable behaviours of the C++11 memory model. But then you've got an issue that you can't write papers about this because there was an issue at the time with how the Isabelle documentation system worked. It wasn't quite powerful enough to do what they wanted. So somebody came up with the idea that actually we should try and extract into Hall, and this person was a Hall expert, so that's why he wanted to do this as well. So he wrote this tool, is-to-Hall. But this is-to-Hall didn't go all the way into Hall, it kind of went into pseudo-Hall. So with some sed scripts, we had to go further. And with another tool, HallDoc, we eventually got some later output that you could use to write papers. But also, he wanted to do some proof. As I said, he was a Hall expert, he didn't want to use Isabelle. So he wrote some more sed scripts, that went into some whole theories, and eventually he did some proof though. And it was a massive mess. And from then on, the idea of LEM, a standalone tool that kind of rationalised all this diagram, was born.
Excuse me, question here. So the proofs in whole were done on translated scripts from Isabel, right?
Yes.
Okay, which were probably not very readable.
Yes, that's a problem.
Okay.
Continue. So what's really needed is a single tool, not a collection of ad hoc set scripts, is a doc or whatever, that, say, it takes in a single model, okay, produces some files that you can do some reasoning on in, say, a theorem prover, produces a model, an executable model in a programming language, but you can run against existing hardware, existing memory models and so on, and produces some documentation that you can take to engineers, you can take to, say, architectural boards and so on, or even write papers with, that nicely pretty prints the model. So the problem statement we have then is, can we increase the amount of model reuse? Can we move to a situation where we just write a model once and then use it to prove properties in multiple backends, so we're not locked into a single theorem prover? Can we write once and validate and execute anywhere, so we can extract to an existing programming language for validation? And in particular, can we make it easier and faster to build these types of models of real-world systems and do the formal methods community a big favour? So before we come up with a solution, we have to take a look at what the type of things that we really wanted to do is. So we have two questions. What should be the input language, and what are the backends, particular backends that we need? And any solution to these two questions is going to be motivated by the types of models that we've already written. So I'm now going to examine 3 of these hardware memory models and so on, and identify some key characteristics that this tool must support to be able to write models like that with them. So the first model is a power and ARM operational model of relaxed memory. So this is developed in Cambridge and also in St Andrews. And this model consists of 2 subcomponents. There's a multiprocessor memory subsystem, and there's a thread semantics that's built on top of that. So this is written in a mix of styles. So there's an abstract machine that uses sets and relations built over lists of memory events, and this is the memory subsystem. That's the style that that's written in. And then there's an abstract syntax tree of assembly microoperation instructions with a label transition system defined using inductive relations, and that's the thread semantics built on top of the memory subsystem. Now this a LaTeX extraction, a LaTeX version, sorry, of this model had been used in the past to talk with the IBM Power engineers, the architects of that architecture. And also an Okawa version of this model had been written, and it's been used as the basis of PPCNet, which is another tool developed in Cambridge for stepping through all the allowable behaviours of the Power platform. And finally, there's been some very preliminary proofs in a COC version of this model. A second model is it's the same model that I showed you before, the big mess. The axiomatic model of the C and C++ allowing concurrency by Mark Batu. So this uses predicates over candidate executions, and these are represented as events. A LaTeX version of this had been used for talking with the C++ standards committee on what the behaviour of the concurrency model in C++ should be, and also been used for talking with ARM and GCC developers, and also a Linux developers conference. An OCaml and HTML version have been used as the basis of that CPP tool. And yeah, as I said, a whole 4 version have been used to explore the meta theory of this model. And the last model is ToCAI. Well, KML is not a model, it's actually a verified compiler for a large subset of the ML language. So this is a joint effort between Cambridge and Kent, hence K. This is written in a mix of styles, so it's inductively defined, relations for the typing, language and bytecode semantics. Whereas the compiler itself is implemented as recursive functions, recursive whole functions, in a typical functional programming style with pattern matching and so on. But it makes heavy use of partial functions which are completely defined within whole for whereas Cork has real issues with them.
Quick question, sorry to keep interrupting. Can you exemplify why does it need partial and not total functions?
Why they need them?
Yeah. Why partiality?
Okay, I don't know, to be honest. So I'm not a member of the Cake development team.
Okay, sure.
I think the issue is that they're all whole developers, and whole, like Isabel, the partiality is completely fine. It gets emulated using undefined or whatever, and that's just how they go about using that tool. Okay, so the whole version of this development have been used in a complete proof of correctness for the entire compiler. So, looking at the commonalities between all of these models, we see that functions, algebraic data types, pattern matching, etc., are all required by them. So what we need is something akin to a typed functional language. But also sets and relations, and the relations can possibly be inductively defined, or required too, to give, say, the KML typing relation. What would be really nice is if there was a library of common data types, say lists, finite maps and so on, that people could just use off the shelf. What we need is a tool that will extract a single model into multiple theme improvers, Hull, Coq, Isabel, and at least one functional programming language. I don't think the fact that it's functional really matters, other than academics tend to use them. For validation and linking with other tools, and also we want to produce nice types of outputs so we can go to the Linux developers or GCC developers and talk to them. But above all, it must be very simple to learn and easy to use. There's no good rewriting a tool that's as complex as an existing proof assistant, otherwise nobody would use it. You might as well just learn proof assistants. So this, of course, necessarily constrains the features the language. We don't want any complex dependent types. So yeah, if you're coming from a hardcore COP or Matita or Raptor background, you're going to be quite disappointed. We've taken the intersection of features, more or less, not the union, to create quite a simple tool.
Excuse me, how do I read this complex dependent types? Is it you don't need any complex dependent types, but you need some dependent types, or dependent types are too complex and they are not needed?
No, dependent types are too complex.
Okay.
Yeah, extracting them into Isabel or Hall 4
is impossible.
Yeah. Okay, so the tool that we came up with was, as you guessed, called Lem. It takes a source language, which I'll describe over the next few slides, and produces Isabel Hall 4 or Coq outputs, depending what you want, or OCaml output for validation, and later the HTML output for communicating or writing papers with. So Lem is a functional programming language with a syntax very similar to OCaml. If you're familiar with OCaml or Haskell, you'll find Lem very easy to read. It's strong, statically typed and polymorphically typed. Features algebraic data types, pattern matching, records, recursive functions, etc. Everything you'd expect from a functional programming language. It also has a very simple type classing system for adaptive polymorphism, for overloading, say, the plus symbol to look at different types. But in addition to the functional programming features, Lem also features inductive relations for describing typing relations, restricted and unrestricted quantification and set comprehensions for talking about membership of sets and so on. And also Lambert assertion statements for talking about the properties of your model and extracting these either as tests that operate on your OCaml generated source code, or lemmers that you can prove by hand within one of the theme improver backends. So just before I describe what LAM looks like, I'm going to point out that LAM is not an alternative foundation of mathematics. If you're coming from an Isabel Cork or whatever background, and you're really interested in consistency and so on, various properties of your foundations, and you're going to be disappointed. So LAM's a pragmatic tool that is meant to replace this SED, this Perl script porting of various models, the hand porting. And in particular, LAM will happily accept code that causes terrible problems in various theme improvers. So, for example, there's partial functions that I've already mentioned. Also, recursive functions may not terminate. So termination is a big issue in all of the theme improver backends. And also non-strictly positive types. Again, these are issues in all theme improvers. So you really have to know what you're doing when you're using LAM. There's no, you can't just press a button and get some amazing output out of it. So here's a taste of LAM, what it looks like. So this is taken from the same model that I was talking about earlier, which is Mark Batty's axiomatic C and C++ 11 concurrency model. So, as you can see, it's very syntactically similar to OCaml or standard ML. So you have tuples, higher order functions, you have nested functions and so on, pattern matching. So everything you'd expect from a functional programming language. But we also have ways to talk about membership of sets, even infinite sets, and also existential and universal quantification, which isn't necessarily computable. Okay. Yeah, and LAM will make an effort as well to try and replace any library functions with existing functions in each of the backends. And this is slightly more complicated than it first seems on the surface, and I'll talk about that later. So this is the OCaml output that's generated from that function. And as you can see, LAM and OCaml are syntactically very similar, so there's not much work really to be done. Apart from the talking about set membership has been replaced by library functions to a pset library. The list.any has been replaced with the native OCaml standard library function list.exists. The pattern matching is kept in place. We also know that there's an attempt at white space preservation. LAM will try hard to keep the code layouts of the original model preserved. It's not always possible in some of the backends, but in OCaml is particularly good at it. So I'll just demonstrate some of the LaTeX outputs as well. So this is a set comprehension. So we're building a set of tuples, of pairs, quantifying over some other set of tuples called HB that's taken as a parameter, and that must satisfy this Boolean condition. Now, if you want to use a typeset version of this in your say your submission to some conference, LAM will generate an auxiliary LaTeX file, and you can just use this macro to include something that looks like that. So it's nicely pre-printed. Okay, I think this is the last demonstration. This is a demonstration of the Isabel whole output. So this is from an ongoing formalization of the ELF file formats, which I'm doing. Yeah, you can see basically it's just a series of nested lets. There's some functions here, there's some record field accesses, and we finish with a multiplication. And LAM very good at preserving the white space in this situation, but the function calls have been replaced by references to functions defined in Isabel libraries. So LAM isn't just doing source-to-source transformations, sorry, string-based transformations. It actually is working quite hard on the source code, and in particular, pattern matching is quite involved. So each of the different backends has a different notion of primitive pattern. So each, say in whole 4, record patterns aren't permitted. whereas in COG, record patterns are perfectly fine. So LEM has to understand each of the pattern capabilities of the back end and stop when it reaches the primitives of that particular back end, or continue and split patterns further when it's analyzing. And also, LEM has to have some quite sophisticated renaming features. Each backend has different reserved keywords, has different library functions that appear in global scope, and so on. So if you reuse one of these names in your existing model and try and extract, LEM has to rename. It also has to know about each of the backend's namespacing to be able to do this properly. And of course, we don't just want to rename to some random name or append a series of numbers on the end of a name. So that all of this is user controlled. The user can override on a per function basis the names that the backend changes things to. Now in particular, it's quite important we map existing LEM types and LEM functions to existing backend primitives. So we want to map the maybe, the LEM maybe type into the option type in Isabelle, option type in vocabulary. This allows us to use a lot of simplification, existing simplification features that Isabelle has on the option type and functions that use it. So again, this isn't just a straightforward matter. You have to take apart functions and give arguments in different order and so on. So if you consider fold right, there's an amazing array of different argument orders in each of the backends for fold right. Some of them take the list first, the function first, and so on. So this all has to be user controlled. We also want to be able to inline various definitions when we think that's the best. So here's an example. This is taken from the LEM list library. So it's the SNOC function, which appends a single element to the tail of a list. But it's given a definition within the library and a type, a polymorphic type. And so we also have these two lines, these two command lines, which instruct LEM on how to extract this. So in the whole for backend, when you extract some whole for code, SNOC will be replaced throughout with the existing SNOC function in the whole for libraries. But if you're extracting to Isabelle or COG, SNOC will be just inlined straight away. There'll be no call at all to SNOC. You'll be replaced with its definition. Or when you extract to the OCaml backend, because there's no overriding mechanism here, this will be extracted as an OCaml function, and SNOC will be called just as a normal function. So LEM is being used quite heavily, not just in Cambridge, but also in Leicester, Kent, NICTA in Australia, Paris and Munich now as well. And I think the use in Munich is the first use that is completely unconnected to anybody in Cambridge. Normally people leave Cambridge and take it with them, take the love for LEM with them, I suppose. So yeah, also LEM generating models are being used internally in ARM. So we have as I mentioned previously, a model of the ARM memory model, and this is used by the ARM compiler developers and the ARM backend of the Linux kernel to work out what the ARM memory model actually is. Also, it's been used to consult with the IBM PowerPC architects. There's quite a lot of conversation on what the PowerPC architecture specification actually says, and it's not at all clear. And they use some of the PowerPC models that have been developed in LEM to guide some of the design decisions within IBM. Also, it's been used to communicate with the C and C++ standards committees, especially some tricky problems with the C and C++ concurrency model. The current standard gets it completely wrong, and there's an ongoing conversation with them as to what that standard should be. and also when writing various academic papers. So just this year alone, LEM is being used in a SQL tool to PPCman, which, as I said, is an operational model for IBM multiprocessor concurrency. Being co-developed in Cambridge and Paris. It's been used in 2 models of ARM multiprocessor concurrency in Cambridge. A SAIL interpreter. So SAIL is a hardware description language which gets translated into LEM for Power and ARM. Not just concurrency, but a total ISA description. And that's been developed in Cambridge as well. Also some extensions to the axiomatic C and C++11 models, trying to resolve the issues that they have there and come up with a better concurrency model. And also a provably equivalent operational model for that concurrency, for that axiomatic model. Also semantics for the thread local behavior of the C programming language called Cerberus. So Cerberus involves a series of transformations into other languages. There's a whole stack of languages which progressively compile features into the next most primitive language until you've got a core of what C is. A new concurrency model for shared memory has been developed in Cambridge. I'm working on the semantics of ELF and linking. Again, I'm at Cambridge. And also a specification of the POSIX file system. A whole family of file systems actually. POSIX isn't that well defined. That's been worked on mostly at Leicester. And of course the KML compiler and syntax, which is being developed well, Kent, NICTA, Cambridge, and also being used at Rockwell Collins as well. And this is all in addition to various existing LEM models that have been developed over the past few years. So models for Power ARM, concurrency and so on. Various compilation schemes for GPUs and so on. Specification of the TCP/IP protocol, the OCaml-like specification and so on. So, I'm going to start concluding. LEM allows users to quickly start writing models. It's straightforward, efficient, and effective. We've got plenty of existing models to demonstrate that. However, there are some small problems that we should be honest about. So LEM's type classes are a bit too simple. So if you're a Haskell programmer and you're used to advanced type classes, then LEMs are going to disappoint. There's no multi-parameter type classes, no functional dependencies, nothing of that sort. You can't also write constructor classes, so you can't capture the monad type class. And also there's no deriving of instances, say for EQ or odd. And for COG, the code generated is often not idiomatic. So I think the quality of code that LEM generates is on a spectrum, with OCaml and Hall and Isabelle on one end, and COG a bit further away on the other. And admittedly, LEM is closer to the whole family of theorem provers in some of the design decisions that it made. And in particular, propositional equality and the impredicativity of LEM's Boolean type are a real problem in the COG backend. However, LEM continues to be developed, bugs fixed, pull requests merged, etc. And this problem with COG, we kind of know how to fix it. It's just an issue of manpower and time that we can't really invest at the moment. And the type classes can be generalized, but again, there's an issue with manpower. And yeah, looking forward, we want to add some more features. So for example, we want to add the ability to randomly test our models using random value generation, like a quick check like that. So to conclude, LEM is a pragmatic tool for engineering semantic models. It's been used